Hello and welcome. Today we'll be dealing with advanced mathematics, so first year typically university maths, multivariable calculus, but it's not actually, I'm not starting a series of lectures on multivariable calculus. I just want to prove this particular result because it is very, very important. It's often used in other bits of maths and it's nice to actually have it there so we see where it's coming from. In fact, it's not just the only result. The Riemann zeta function of 2 is another one that is really nice to know, not just its value, that is pi squared over 6 of course, but also where it's coming from. There's a couple of different ways we can do this one. What's the other one? Then the integral sine of x over x from 0 to infinity, which is of course pi over 2. It's another one that it comes up in many different places of mathematics, and it's nice to have seen where it's coming from so we can quote it. Okay, we're going to start with this. What kind of knowledge is actually required in order to follow this particular lecture? You need multivariable calculus in Cartesian and in plane polar coordinates, and pretty much that is it. So if it's typically, as I said, university maths year 1 perhaps, and if you do a little bit of reading perhaps on sort of like double integration and a little bit on polar coordinates, maybe you can follow this. Otherwise it's really for university students pretty much. Okay, so we're going to look at this particular result, and keep in mind, if we need it from minus infinity to infinity, because we've got an even integrand in there, the answer is simply the square root of pi. So I'm going to do it from 0 to infinity today. So how we're going to do that is we're going to define as I being the above integral, the integral from 0 to infinity e to the minus x squared dx. I'm also going to write a little property that we ought to be using in here, so that kind of thing makes sense. If we have an integral from a to b of f of x dx, whatever is the numerical value of that, and we are going to multiply it by another integral, again with constant coefficients, c to d, but this is a g of y dy, then the answer is simply a double integral. The order of integration doesn't really matter, so we can write it f times g or g times f, g of y. I'm going to do it as dx dy here, and of course the limits in x, which I'm doing first as I've written it, is a to b and c to d. So we can use that backwards or forwards. We're going to need to use this particular one for this proof. So where do we start? Well, we define this integral as I, so I will also be equal to, because this is a dummy variable, so numerically if we were to change the x for, I don't know, t, y, whatever you want to call it, it would have been exactly the same. So this is also I. Okay, that's good. So if we multiply our two integrals together, I times I, quite clearly we're going to get, I'm going to use for the first I this expression here, 0 to infinity e to the minus x squared dx. And for the second I, I'm going to use the integral in y. That's definitely sound. So we go e to the minus y squared dy. And now by the property that I've just written up there, this is your f of x, this is your g of y. The limits are constant. So I can actually write as a single double integral, and it's e to the minus x squared multiplying e to the minus y squared dx dy with limits. Let's put x and y at the bottom, 0 and infinities at the top. So far so good. So I can actually write further, well, whatever the value of this quantity is, I squared now, is going to be equal to the integral, the double integral, which runs from x is equal to 0 to infinity, y equal to 0 to infinity of e, and I'm going to write this as a single exponential, minus x squared plus y squared dx dy. Now, is this a difficult integral to do? Well, in Cartesian it is. You can try perhaps a few substitutions, a few manipulations. I don't think many things will work in there. So, but we notice this term x squared plus y squared, which is very, very common in polar coordinates. Of course, it is known to be r squared. And let's look at the integration region. So this is now on a xy plane. The Cartesian region is from x is equal to 0 to infinity, so it's all of that if you want. And in y is above the above the x-axis. So we are entirely in the first quadrant, on the top right if you want. If we change into polar coordinates, this will be very, very easy. First of all, the x squared plus y squared will be equal to r squared. The limits will run, the r will be between 0 and infinity. So the radius vector, if you want, in order to sweep that area, needs to go from the origin forever to the right, if you want, or away from the origin, not to the right, to the away from the origin. And the theta that needs to be swept is from 0 to pi over 2. So like this. So this angle here. How about the dx dy? So that's going to be e to the minus r squared. We'll change the limits. This is like a substitution now. The Jacobian, as is known, for transforming from Cartesian into polar, it's a very well-known Jacobian. We don't even need to prove it. We can take it as a given. Is dx dy is equal to r. Let me move out of the way, move that cable as well with me. Is dx dy is equal to r dr d theta. So that's the element dx dy which I've just got in there. Let's see now how this will change as we're moving into polar coordinates. So from r is equal to 0 to infinity, and from theta is equal to 0 to pi over 2. This is the limits which define again the very same region that we got in there. We're going to have a minus r squared. That's the x squared plus y squared, and the element dx dy is now producing an extra r, and this is vital in order to do our work. So r dr d theta. Can we do the integration by splitting it into two separate integrals by using the rule we just wrote in the very beginning? The answer is yes, we can. Or we can do it as a double integral as per standard, the standard way, if you, as we know it. So how will I do this one? So this, don't forget, is I squared. So let me just write again on the top. I squared is equal to, let me just split it back, because of course the limits are constant. There's no kind of like a plus in the middle. Let's, for example, if we had an r e to the minus r squared plus a theta, we could not split it, because this it cannot be split as a function of r and a function of theta. So here we can actually split it into two separate integrals again. So 0 to pi over 2, and that's my d theta 1, multiplying the integral from 0 to infinity. That's my dr integral, and the function of r is going to be r e to the minus r squared. The function of theta, of course, is just a constant 1. And these two things now integrate very, very nicely and very, very easily. Of course, integrating 1 from 0 to pi over 2 should give us pi over 2. And this r that we have in front of the exponential makes all the difference. So integrating now is going to be, of course, an e to the minus r squared. On differentiation, we get now a minus 2r. We got the r, so we need to get rid of the minus 2. We need the minus a half in front of it. Limits, of course, from 0 to infinity. I'm not going to do things formally there by taking limits or anything like that. We're going to do it the applied mathematician's way. So, and also I prefer to just lose this into a plus and reverse the limits. My brain finds it easier to do it this way. So when I put the top limit, which of course is e to the 0, what I'm getting is just half. And when I let r tend to infinity, because of the negative on the exponent in there, the whole thing vanishes, and we've got this expression here. And we're practically done now. we found that the value that we're after is pi over 4, and therefore the particular integral which has a positive value, because of course you might say, how come I don't take the negative square root? The e to the minus x squared is of course something which looks like this. It's entirely positive, and how I have it up there is of course from 0 to infinity. It's just this section here, so this is definitely a positive number, so it's the positive square root of the square root of pi over 2, and we're done. Of course the whole thing is the square root of pi. Okay, I hope you found it useful and you followed what I've done in there. I don't think this is particularly difficult. I think it's quite straightforward if you know your basic stuff from the multivariable calculus. Okay, I'll see you very soon, and who's laughing now?